Hey guys, welcome to Getting Science. Today we're going to try and figure out what density is. And we're going to melt some metal.
You blow my mind. I don't know if you know yet. I've tried some time, and I'm dying to tell you. You blow my mind. I don't know if you know yet. I've realized, and I'm dying to tell you.
Here I have examples of three different metals: lead, aluminium, tin. They're all kind of silvery grey in color, but lead is the heaviest, aluminium is the lightest, and tin is sort of in between. We can see that the lead is thin compared to the aluminium, and roughly the same diameter but a lot thinner. So the lead is the smallest, much smaller than the aluminium, and yet it's the heaviest. Why is that? The ratio of mass per volume is what we call density. Mass divided by volume. Grams per cubic centimeter or grams per milliliter is the density. Lead has a much higher density than aluminium. Let's see if we can measure the density for these three metals. So first we'll measure the mass of each sample of metal. First the lead, 83.4 grams. Then the tin, 70.72 grams. And then the aluminium, 49.57 grams. Okay, so now we're going to measure the volume of each sample. We're going to do that by measuring the amount of water that each sample displaces. So here I have a beaker that is inclined at an angle and filled to the brim with water. Anything I add to this now is going to cause water to overflow, and I'm going to catch that water in this measuring cylinder, and then we'll see exactly how much water is displaced. The amount of water is displaced will equal the volume of each sample. So I'm going to take the aluminium first, and I'm going to carefully lower it into this beaker. And we're going to capture the water that's displaced. And now for the tin, we'll repeat the same process. So this method using the beaker wasn't working so well because dropping a chunk of metal into the beaker was causing too much water to dribble down the side of the beaker, and it wasn't being collected by the measuring cylinder. So I decided to use an alternative method where the sample is suspended in a beaker of water and the mass of the displaced water is measured by the scale. And it so happens that that is directly equal to the volume of the sample, and that uses the principle of buoyancy force, which we will get into in another video. Okay, so now we're going to measure the volume using a slightly different method. First the aluminium, I'm going to dunk it in water, and the scale reads 18.66. Now the tin, 9.69, and now the lead, 7.51. So to recap, we've defined density as mass divided by volume. We've measured the mass in grams for three different samples and the volume in milliliters. And the samples are aluminium, tin, and lead. Masses as recorded and volumes as well. So now we can calculate the density by, for aluminium for example, we can take the mass of 49.57 grams and divide it by the volume of 18.66 milliliters, giving us a value of 2.66 grams per milliliter. Doing the same thing for tin, giving us a density of 7.3, and lead 11.11 grams per milliliter. So now we can see that yes, lead has a much higher density than aluminium, and tin is somewhere in between. When we combine two or more metals, we create a mixture of metals, which we call alloys. So we can define an alloy as a combination of two or more metals, and sometimes other substances, because sometimes non-metals are mixed in also. I'm going to make a mixture of two metals by mixing my sample of tin with the aluminium. Okay, so now we're going to take our two metals, aluminium and tin, and we're going to melt them, mix them together, and make a new metal mixture which we're going to cast into this little mold. I'm just going to use this steel crucible, and I'm going to heat that over a small gas burner. Hopefully we'll get enough heat. The aluminium melts at about 660 degrees Celsius, so I'll put that in first. Once that's all molten, then I'll add the tin, so that should melt quite easily. Mix the two together, and then we'll cast them in this little mold that we have. Okay, that's the new metal mixture ingot that we have just molded. It's still, it hasn't completely solidified, so we're going to give that a few minutes to cool down. Okay, so now we're going to measure the mass of our new sample. 107.07 grams. Now we're going to measure the volume. 25.38 milliliters. Okay, so calculating the density of our new alloy, our combination of tin and aluminium, we measured a mass of 107.07 grams and a volume of 25.38 mils. The mass divided by the volume gives us a density of 4.22 grams per milliliter. And we see that yes, that is in between the density of pure aluminium and density of pure tin. The question now is it possible, using this value of density, to determine what percentage of our metal alloy, of our metal mixture, is made up of aluminium and what percentage is tin? Well, the answer to that question is yes, of course. Let's assume that this circle represents our mixture of the two metals, and the orange sector is the aluminium, for example, and what's left would therefore have to be the tin. If we then said that the fraction of the volume, which is the aluminium, in this picture it looks like it could be 3/4, but we don't know. We want to calculate what that fraction is. If we say we let that fraction be the variable x, then the remaining portion of our sample would be 1, being the whole, minus x. That allows us to formulate an equation. The mass of the aluminium will be the volume fraction x multiplied by the density of the aluminium. That symbol there is the Greek symbol rho, which is the symbol that we use for density. So the volume fraction times the density of the aluminium, plus the volume fraction of the tin, which is 1 minus x, times the density of the tin. That must equal the new density of our mixture of the two metals, or the density of the alloy. Substituting in the numbers that we have, the volume fraction x times the density of the aluminium, 2.66, plus 1 minus x times the density of the tin, will equal 4.22, which is the new density of the alloy that we measured. Solving for x in this equation gives us x times 4.64 equal to 3.08, and therefore x is equal to 0.66. That means 66% of our alloy is actually aluminium, approximately 2/3. Therefore, the remaining 34% is tin. And so, by using the physical property of density, we have been able to determine the composition of our mixture of metals. Hey guys, I hope you found this video helpful. If so, please click like, subscribe, comment, share. And remember, don't stop getting it until you've got it. See you next time.